Okay, let's go ahead and get started. One announcement is office hours for me are posted on the course webpage. I'm doing office hours Wednesdays, so tomorrow will be the first one at 3 o'clock, 3 to 4 p.m. And my office is Rice 306. So feel free to stop by if you have questions about anything, homework or otherwise. I think Amon will add office hours when he gets a room scheduled. We'll have another time slot that you can take advantage of. Okay. Any questions of logistics of the course or anything before we get started? Okay. So today our goal, just to give a maybe quick pointer to where we are in the schedule. So today we're trying to finish topology. We'll probably finish topology. This is section 1 in the notes that are on the class webpage. And starting on Thursday, we'll move to differentiable manifolds. So we'll talk about what it means to be a manifold. And some of the topological concepts we're talking about last time and today will come up in the definition of a manifold. Amon will be taking over on Thursday to do the next section, which is in the notes in section 3 on differentiable manifold. But before that, we'll try to finish topology today. Okay, so I mentioned at the outset of our discussion of topology that one of the motivations for the definition, we saw the axiomatic definition of what it means to be a topological space, was to generalize the concept of continuity of functions. So we're all familiar with continuous functions. Our definition we learned back in usually in calculus 1, very early on in calc 1, we learned about what it means for a real valued function to be continuous. Okay, so let's start out with, I don't think, I might do a little bit later, but I won't, at the beginning here, I won't review the technical definition of what it means to be a continuous function. But let's just review the intuition for what it means to be a continuous function, because we're going to make it a more abstract concept in terms of topological spaces. And the intuition will be more, hopefully more readily seen than the actual connection to the technical definition. So let's think about a function, again, as we're most often familiar with a real valued function taking the real line to the real line. Can anybody volunteer what a intuitive definition, what it means to be continuous? Don't use any mathy language per se. Try to be very intuitive about no epsilons and deltas. What do you think? Can you define? So far in the back is the first hand up.
I will use limits. So
you're going to use limits.
Well, kind of. It's not technical.
Okay. Can you do it without? I'm going to do it without limits or epsilons and deltas.
Just intuitive. The function will be defined at every point of the domain. Like.
Okay, not quite enough because I can function. Okay, go ahead.
If you draw, like, if you take a pencil and will draw across the function, it should be a sweep motion without like any jumps.
Cool, great, perfect. Yeah, great. That's a great intuitive definition. So if I were to draw the graph of this function, I'm not going to jump, and I'll kind of add to that. What that means is I'm not going to let the let's do it. Let's have x and f of x. I'm going to draw the graph of a function. I'm going to make a motion where I don't let the chalk come off the board and jump to a higher or lower point. I got to keep the chalk on the board. That's one way to say it. Okay. Oops, sorry. The Zoom people, I tend to wander off and the camera takes it. Okay. Yeah. So that I think was kind of the definition, roughly, intuition I had in mind. Anybody want to say something different than that, or that's again an intuitive way of thinking of continuity? Now, of course, if it's defining the whole real line, I would need to, maybe have two arms that have infinite length that can go out to infinity. So I can't do that. But with any bounded interval, I can draw a continuous function by keeping my chalk on the board and never letting it jump. I of course I wouldn't backtrack, because if I backtrack like something like that, it's not a well-defined function. I can't have two values at the same x input. So to be well-defined, I can only have one point of its sign to every x. But the other point I want to make is that I drew this as a smooth curve, more or less. It doesn't have to be smooth, as long as I'm not taking the chalk off the board. I can have these sharp corners in it. That's all fine. So it doesn't have to be even differentiable. It can have sharp changes, but it does have to be, in a sense, connected there. Okay. So continuity has this, at least when you think of the graph of a function, has this sort of connectedness is part of the property here, and it's a topological property of the function here. Okay, so yeah, so now, as we've been talking about, let's say I have two topological spaces instead of the real line. What I want to do is generalize this concept of continuity to having a topological space X as my inputs and a topological space Y as my outputs to my function. And of course, any sets, I can define functions between sets. It's something that a function is something that takes inputs here in the input set and assigns a unique value to each input in the Y set. So function as a set operation is all good and well. And now if I, in addition to X and Y being sets, say they have a topology on them. And remember, the topology just means we define which subsets of these sets we'll call open. They have to satisfy those three axioms. And what does it mean now for this function f between topological spaces to be a continuous function is the goal. Okay, any questions so far? All right, cool. So let's make sure the camera tracks and talk about the definition of continuity. So yeah, for this same setup, this function f between two topological spaces x and y. Is continuous if, I'm going to write this out a little bit longer than I think the notes say it, the inverse image I'll explain this a little bit more just to remind everybody what we mean by inverse image, but F inverse of U for any open set U in Y is open in X. I just wrote the whole thing down, but let's take it slowly in each piece here. So if I have this function between two topological spaces, if I give you an open set U in the topology of Y, and then I take its inverse image, And let me expand on that. I don't mean that F is invertible, so this is a little bit of a abusive notation, but that mathematicians use, not just me using the notation here, but F inverse of U, the inverse image, F does not have to be invertible. And what this means is that this is all points X in the input, in the domain, such that the output of F is in the set I'm taking the inverse image of. With all points in the input domain that map into U. Okay, so everything in X that maps into U is going to be this set F inverse of U. And to be continuous, I'm requiring that this inverse image of any open set of Y is open in the input domain X. Okay, and that's the definition of continuous. Any questions there? Okay, maybe drawing a picture. I've got a space X and a space Y, and I have a mapping F between them. If I give you an open set U in the output space, then I can imagine that there's a set F inverse of U, and this means that any point here, any point X here is going to map to some point F of X inside of U. And basically every point here is going to end up landing somewhere inside of U. I need this set to be open. And this has to hold for any choice of open set U in the output space Y. Okay. And so let's think again about intuition of what exactly it means to be continuous. And again, thinking about our continuous functions of the real line. What do we mean when we say a function is continuous? Where we had the graph is something that I keep my chalk down and can't make any jumps. And a jump in the output is a discontinuity in the output. What do we mean there? It means if I had a little open set about a point, then the inverse image, right, would not be an open set anymore because it has this kind of sharp boundary to it. Okay, and another way of thinking about this is, as we know, like a continuous function, what we mean is that any kind of changes, connection in the input is going to stay connected in the output. And so remember, open sets it's not a perfect analogy, but open sets we can think of as neighborhoods of points. Because with the topology, we have no notion of closeness. There's no distance. We're going to talk about distance metrics in a little bit here, but from a just generic topology with the three axioms, there's no distance in the space. But we can talk about a neighborhood of how close I shouldn't say close, but a neighborhood of things in my neighborhood. You can think of open sets as a generalization of neighborhood that you think of when you think of like an open ball in Euclidean space being a neighborhood of who's close. And so this notion of closeness or connectedness, we make it more abstract and more broad, and we talk about just openness of sets. And we need the open sets to kind of have this property as you map them back and forth here in for a function to be continuous is the idea. Okay. So any questions about continuous? Yeah.
X and Y, are they just arbitrary sets or are these topologies?
They're topological spaces, yeah. So they have to be sets with a topology on them. So I could say X and Y in the following way, where X has a topology along with it, and Y has a topology with it. And just remember that this T, I'm putting a subscript X because there's two topologies here. The TX here means it's a set of sets a set of subsets of X that I'm declaring to be open sets. And I can't declare any old collection of sets. They have to satisfy those three axioms that the null set, the full set X have to be in the topology in the open sets. Arbitrary unions have to be also open, and then finite intersections of open sets have to be open. So those three axioms we talked about on last Thursday, they have to hold here for Tx and Ty. So yeah, there's these sets with topologies or topological spaces. Yeah. Okay. Right. So the definition is fairly abstract, and it really seems a little bit tricky because we have to go through this. We don't talk about if I take an open set in the input, what it does in the output. We have no specification what open set in the input has to do. We take it kind of in the reverse direction of F. We say if you have an open set in the output, its inverse image, all the things that map into it from the input have to be form an open set. Okay. And in a minute here, I'm going to go through to make the connection to what you do know already, the epsilon delta definition, and we'll see it's not completely obvious where the epsilon delta thing would have any relationship to this definition. Maybe you can kind of see the connections a little bit, but we'll make it a little more precise here in a minute, that connection. Yeah, but are there any other questions about the definition? Yes.
Sir, I have a question. Fortunately, I asked like a closed set for input and output is also closed set. Could it follow the definition, or what kind of rules it violated?
So you're asking, is the definition equivalent to saying any closed set in the input has to map to a closed set in the output? Is that the question? That's a good question. I think that's not quite equivalent. Let's see if I can. I mean, I'd have to give a counterexample to show. It may be tricky, but I don't think that's quite equivalent. So things that map closed sets to closed sets are called closed mappings. Things that map open sets to open sets are called open mappings, but that's not equivalent to going in the forward direction. So yeah, so I'd have to maybe think more to give you a better answer, but yeah. I do have an answer, maybe as a preview here. I do have an answer to the question last week about why the null set has to be in the set of open sets. So just as a, we'll see in a minute. I thought it probably broke continuity. It breaks continuity if you don't have. I'll show in a minute here. Okay. Other questions about the definition? Okay, let's make the connection here. Sorry, let me. To our usual epsilon delta definition. So if you remember, I won't write the whole definition out. I'll just kind of draw a picture here. So let me just remind everyone that the epsilon delta definition to say that a function when your topological spaces are the real numbers, if x was r and y was r. So this is you really just need the topology of r. That's all you need to call this, function either continuous or not continuous. Remember the epsilon delta definition is that I'm going to say this has to hold at every point. I have some input x here, let's say, and it will map to some point f of x, right? And the epsilon delta definition, and sorry for the camera again, says that for any epsilon, if I take a little window, a little open interval about the output f of x, and that's going to be f of x plus epsilon, f of x minus epsilon, right? that there exists a delta. Draw this a little bit better so that I could make this window here. There exists a delta back down here in X space that an open interval about X of radius delta is contained that maps fully into this epsilon window here, if you will. So I can find a delta. So let's say this is X plus delta, X minus delta. Again, open interval. This is less, it's usually written as, you know, X that this distance from, you know, any point, I should call this maybe X naught, it's usual way of saying it. Any X in this radius delta open interval. So the distance between X naught X, the X's are less than delta here. That is completely contained in this epsilon window in the output. Okay, that's the usual epsilon delta definition of continuity. So first thing to notice is that this definition isn't talking about any open set, right? Open sets, remember, could be unions of open intervals in the real line. So it's very specifically talking about only single intervals here and here. But remember when we talked about a basis for the topology R, we said that open intervals were basically, we call them balls of some radius. And this is a ball centered at f of x of radius epsilon, an open ball in the real line. And this is an open ball in the real line here. So what it's saying is that if you give me an open ball, in other words, any basis element in the output domain in the line, I can find an open ball, a basis element that's in the inverse image of this open ball. Okay, so it is an inverse image openness, but it's working in the basis. Okay, and what I'll do is I'll now wave my hands a little bit. I won't give the full proof, but I'll encourage you to think about it after class. You can show that if this holds for every basis element in your topology, then it holds for all open sets in your topology. Okay. And what you need maybe to remember, maybe I'll take you one step towards that, to the argument, is to remember that if you have a basis for your topological space, let's talk about the space X, about the basis for the topological space X, what that means is that any open set, let's have a U, which is a subset, I guess I'm kind of leaving this off for now, a subset of our topological space X. It means that at any point in U, I can find a basis element B that's fully contained in U. So any open set, I can always, because remember, every open set's made up of a union of basis elements. So give me an open set, I can always find at any point a basis element that's completely contained in that open set. Okay. If you think about the implications of that, you could show that this would hold if I had any open set. I could just make arguments with if it holds for basis elements, I can make argument that it holds the same thing that we have the definition here for any open sets. Okay. So yeah, and the one thing I'll point out when we talk about open sets being neighborhoods of points, and continuity saying something about if I'm in some neighborhood of the output, it means that there's a neighborhood around the input that stays within that output neighborhood. That's kind of the way to think of continuity on the real line. The basis elements are probably a little bit better generalization of a neighborhood, because in the real line, when we talk about neighborhood, a closeness, the concept of closeness, it's this metric ball, it's this open intervals around a point. Okay. Okay, any questions? So hopefully that starts to make this concept of continuity that's more general between topological spaces. To see what exactly is it generalizing from our usual concept of continuity. Yeah.
This might be a bad question, but
There's no bad questions. Go ahead.
like, how do you get the inverse of a topological space? I was kind of not getting my head around it.
Yeah, so this line right here, right? The inverse of the F inverse of U. Yeah, so let me again, this thing is very confusing, I think, also. Yeah, but let me sort of reiterate. This is what's called the inverse image. Okay, and it's not the inverse function of F as a function. So if F, because F may not be, remember, the only time you can invert a function is if it's a bijection, right? And so F can be like our continuous functions on the real line. They don't have, like the sine function is not invertible, right? But it's continuous. So the F does not have to be continuous. I mean, sorry, invertible. But the notation, unfortunately, if I just look at this part of it, is the same. F inverse looks like the inverse of a function. But what we mean by this, when I put parentheses and then a set, this will be a set. This U is a subset of the output. So it's a subset of Y. And so if I say F inverse of U, what I really mean is a specific set in the input space. And it really means all the points in the input space that map into this output set U. So if I kind of were to draw little arrows here, this would map here. Every point I would pick would map somewhere into this target set U, is what I mean. And every point you can find here that does that is included in this set definition of inverse of U. Okay, does that help? Yeah, so in just a moment, I'm going to overload this notation, talk about bijections and their inverses. So be careful. It'll be clear from context, but we have to be careful to not get tripped up between the inverse of a function and of any function's inverse image. Okay. Right. So I think that was all the points I wanted to make about the connection to continuity in real value functions. Yeah, so to that point about bijections, let me talk about that now. So one of the things that we're going to do in the class going forward is I mentioned this concept of when two topological spaces are equivalent. We saw like the little cow toy blown up to a sphere. Those were the equivalent topological spaces. And I made this, again, intuition that if you take a space and think of it as made out of like kind of like a clay or pliable like rubber or something, you can stretch it, squish it, but you just can't tear it. This is the notion of two topological spaces being equivalent. And notice this continuity starts to talk about when we have a discontinuity is like a tear in your space. So if you had a discontinuous function, you're somehow changing the topology is the point. So now we can talk about more specifically what we mean by two spaces being topologically equivalent. And we call that homeomorphism. So homeomorphism is between two topological spaces. Topological spaces. And again, I'll leave off the topologies. I'll just say X and Y. I'll leave off the TX and TY. It's a bijective mapping. And I'll kind of use the word mapping and function interchangeably, by the way. For some reason, I think when you talk about a function from a space to another space. I like the word mapping better, but anyway, it's, you know, tomato, tomato. So the bijective mapping F from X to Y. So now F is bijective as a function between two sets. So it does have an inverse. Okay, honest to goodness, F inverse, right? And now to be a homeomorphism, I need F such that F is continuous. And the inverse mapping, which is unfortunately the same notation, F inverse, but notice I don't say of U, just F inverse is now the inverse function. Its inverse, F inverse, is also continuous. Okay. So to be a homeomorphism between X and Y, again, I'm going to have a mapping between X and Y, which is bijective. So bijective, just to recall, what does this mean? It means it's onto. Onto, remember, means that every single point of Y is hit by some input point, F of X. And it also is 1-to-1. That means that there can't be 2 points in the input X that map to the same point in Y. Okay, so 1-to-1 and onto, right, gives you a bijection. Another way to think of this, there's a 1-to-1 correspondence back and forth between X and Y, right? Every point here goes to the unique point here and can get back to where it came from. Okay. So yeah, you have this bijection. And by the way, bijection is the set theory concept of equivalence, right? Two sets are basically as sets equivalent because the set has no other structure to it. It doesn't have any algebra or topology or anything or calculus associated with it. It's just a list of points. If you have a bijection between two sets, then as far as set theory goes, they're the same set. So homeomorphism is now the kind of analogous concept for topology. If I have two topological spaces, they have to be equivalent as sets, so they have to be bijectively in correspondence with each other, but they also have to have the same topological structure, the same open sets. And for that to be the case, I need this bijection to be continuous and its inverse to be continuous. Okay. And we're going to get more words that have morphism in them. There will be equivalence between other structures, like when we talked about manifold and Riemannian manifolds and so forth. We're going to also have equivalences between those mathematical structures as well. Okay. So quick example of a homeomorphism is the following. Coming back to this picture of a function from the real line to itself. This graph of F is a homeomorphism from the real line to this curve thought of as a set by itself. So if you take this curve, it's kind of a subset of R2, the plane. It is homeomorphic to the real line if F is continuous. Now, of course, I said F inverse has to exist and that has to be continuous. But you, again, I'm going to wave my hands and say, try to prove this yourself if you're interested in being super rigorous about it. If you have any, function as a graph, you can invert it just by projecting back down to the X component. So this graph is really the set X, F of X for all X on the real line, right? And this is kind of a subset of the two plane. To get back from this graph back to X, you just delete the F of X part and project back to the X. Okay, and that inverse, I'm going to claim, is really F inverse of the mapping from the real line to the graph, and that's also a continuous function. It's pretty easy to see if you remember. Sorry, I keep swapping the board. If you remember your kind of calculus and so forth. So anyway, and intuitively, this makes a lot of sense. If you think about this line as a string, and I'm just kind of pushing the string, maybe it's got a rubber band because I got to stretch it to do this. I'm going to push it up to the height I need to be F of X. I'm not making any tears or adding any new components to anything. And then I'm taking that rubber band and relaxing and pushing it back into the real line. That I can kind of do that forward and backwards. And so this curve is topologically the same as the straight x-axis curve. Okay. And it's actually the case that even if this isn't the real line, but this is two topological spaces, and I'm thinking of this, as a point in X and f of X as a point in Y, and this is a ordered pair in the direct product between X and Y. Then this graph is homeomorphic to the space, the input space X. So this works for all topological spaces, not just the real line. This graph of functions are homeomorphic to the input space that you have. Okay, so that's an example of a homeomorphism. Let's see, any questions about continuity or homeomorphisms? All right, is that a question?
Yeah.
go
So actually, I have a question. If we apply the theorem, the epsilon delta theorem to the topological space.
So let's be careful. I want to be careful. Epsilon delta is a definition, and it only holds for Euclidean space, like R. It actually holds for R of some dimension, like a multivariate mapping. But let's just say for real lines. But yeah, go ahead.
Yeah, I mean, I apply it into two-dimensional. I mean, the epsilon delta is the space size or its position.
The epsilon is really a width or a distance, if you will, on the real line that we talk about here. So here it's that f of x naught. But this is really the distance that f of x, the distance between the kind of center point here and any other x has to be less than epsilon. The epsilon is kind of like the radius or the distance you're allowed to move here. And same thing with delta. The delta is just on the downstairs of the input space x. Does that make sense? So the position is this x naught. F of x naught here is the position there. The epsilon and delta are just kind of a radius about those positions. Okay. Yeah.
You said this function f is a homeomorphism between the real line and the real line.
The graph, I have to be careful. I might have said that and that would have been incorrect. F is not the homeomorphism, it's the mapping to the graph. So this is actually not exactly the same. So this is like the mapping. I take a point X and I map it to the ordered pair X comma f of X. That mapping, and I have to be careful, it's the mapping not to all of R2, but the mapping to the output, which is this curve itself as a set, which is the full image of the real line under this mapping, is homeomorphic to the real line. Yeah. So this mapping you could think of is, oh yeah, this is a mapping from R to R2. But of course you can't, it's not onto, right? But it is onto the image of this mapping, which is just the curve itself. So this curve as kind of a subspace of R2 is homeomorphic to the real line. Yeah. So it's a little bit tricky. I might have been a little bit too fast and loose with how I said it. Yeah. But the intuition hopefully is clear that like if I take this as a kind of string and I can take this as a string or stretchable string that can move back and forth, and those are the kind of the same topological space. And it wouldn't matter if I put, like a pin here and they have a nice sharp corner in my string, that's still okay. I can still map that back and forth because the corners don't matter. But if I did something, with a gap in it, like so, like a jump, that would be a problem. Yeah.
The same intuition as you showed before, the torus and the graph, and you can just, if it takes a line, you just
Yeah.
straight it into the
Exactly. So yeah, always keep in mind in topology, exactly that tuition is I can just move things around. And like you said, the torus in the cup, I can move things around, I can push things and stretch things and squeeze things. I just can't tear things. I can't poke holes in things. And I can't add things typically. Like I couldn't add another handle to the coffee mug. I'd have a different topology. Okay. All right. So I'm just gonna, I forgot to actually bring up my notes to just make sure I don't forget a topic to or that we need to cover in today's list. Okay, good. That's everything I had for continuity. So the a couple of other things to talk about. Yeah, question, go ahead.
So you mentioned that f of x is homeomorphic to x-axis, right? So it's also homeomorphic to y-axis as well, right?
Yeah, this is also homeomorphic to the y-axis. It's just not this graph is it's not a direct, this is directly a homeomorphism to the x-axis, because if this is the x, there's not really a direct homeomorphism here to the y-axis, because the function may not cover the whole y-axis. This would be a homeomorphism to the y-axis if f is either monotonic increasing or monotonic decreasing, and you hit every point in the y-axis. So yeah, like we said, the sine function is a good example. It's something like this, where I only hit values between -1 and 1. And so, 2 would have no point to map to. So you're right that the y-axis has the same topology as the x-axis. They're both a real line. So it is homeomorphic. It's just that this mapping isn't the thing that shows it's homeomorphic. Yeah, directly. Okay. Yeah, so a couple of other concepts to cover. Maybe 3 more concepts I think I need to try to get to today. And oh, actually, no, I know I'm forgetting. I knew there was something I'm forgetting. The question from last time about why is the null set in the topology definition? Why does the null set have to be open? I actually asked ChatGPT. I came up with an answer, and then I asked ChatGPT. It initially gave me a bunch of garbly, vague things like, oh yeah, of course it has to be open, blah, blah, blah. But eventually I asked a follow-up question. I was like, can you be more specific? Something like that. And it actually gave me this same answer that I'm going to give you. So I was impressed. It took ChatGPT a little bit of time. It had to think about it, but it came up with the right, what I think is the best answer. So why does the null set have to be open? So again, because topology, the main motivation of topology is to generalize this notion of continuity. If we look at the definition over there of continuous, take the following example. I'll draw it instead of writing words. Again, X, just any topological space, and you can think the real line if this helps. And Y, also any topological space. And now let's say I have a function F, which maps always to a constant point Y. So for any X, Y is always this single point. Is f of x for any x. Okay, so this whole space just always maps to one point. Okay, intuitively, we would like that to be a continuous function, right? You would call that, like, if you think about the real line, the function that just maps you always to the same y output would be just a straight horizontal line, right? It's continuous because changes over here don't do anything over here. It kind of keeps the neighborhood together, if you will. And you notice with our current definition, everything works out great because any open set either contains y or doesn't contain y. The ones that contain y, the inverse image is all of x, and that's open. The ones that don't contain Y, the inverse image is the null set. Right, if this is our open set U here, that doesn't intersect Y, the inverse image of this is all points that map into U, and that's nothing. So it's the null set. Now, if we didn't have the null set as an open set over here, then we'd have this function wouldn't be continuous, which would be very weird to have a function that doesn't change anything, just always stays put, not be a continuous thing. You could also think of other examples, like if I come back again one more time to, oh, sorry, the board had skipped over. I hope people on Zoom saw that example. Keep it there for a second. This set that doesn't contain Y, inverse image is the null set. That's why null needs to be open. And just to give one more example, if we think again of the sine function, so it don't have to be a constant function, that's a very specific example, but something like the sine function or any other function really that doesn't fill up your whole Y space is all I need. Is for any function that doesn't fill up the entire Y space, there's going to be an open set, like say over here, that doesn't intersect your output set, your image of your function, and the inverse image of that set, because it doesn't intersect my sine wave over here, is going to be the null set. So really any function could not be continuous unless it filled up the entire output space. And so that would, you know, invalidate a lot of functions that we would like to be continuous. So that's the real motivation why we want the null set to be open. Okay. I think it breaks other things in topology, but that's the one I could think of that's really the most obvious one. And ChatGPT also thought of it. So, okay, great. So that's everything on continuity. The next thing I want to cover is, again, a sort of, you know, generalization of things we're used to in Euclidean space, but they will come up when we talk about Riemannian geometry. But we can talk about them specifically with just topology for the time being. And that's the concept of a distance or a metric. So, and you've probably seen this concept of a formal, you know, mathematical definition of what it means to be a distance function. But if you have seen it, this will be reviewed. If you haven't seen it, that's okay. I'm going to call it a metric. I could also just call this a distance function. If you prefer to call it that, but if you hear me say metric, I mean this. So a metric or a distance function on a set, and this doesn't have to be a topology, just a set, X is a function D, which takes 2 points in your set X and returns a number, a real number, greater than or equal to 0, so no negative numbers allowed. And it has to satisfy 3 rules. Number 1, it has to be the case that dxy is greater than 0 if x doesn't equal y, and equal to 0 if you give it x and y being the same point. Okay, so point is always distance 0 to itself. If they're unique points, so they're not the same point, they can't have 0 distance, they have to have some positive, strictly positive distance. Rule number 2 is symmetry. So this function, if I flip the role, of x and y, I'll get the same distance. Distance to x, y is the same as distance to y to x. Okay, that's pretty natural. Again, our intuitive thinking of what needs to be a distance. And then the third one is always the sticky point. That's hard to show for most distance functions is the triangle inequality. And this says that the distance from X to Y plus the distance then from Y to another point Z is always greater or equal to the direct distance from X to Z. And of course, this is triangle inequality because if you drew kind of a picture going from the distance between X and Y first, and then I'm adding, if I traveled from Y to Z, and just like in Euclidean geometry in the plane, same thing holds in this abstract definition of distances. That's always going to be at least as long, if not longer, than taking the straight path distance from X to Z. Now, if they straight path, then of course, there's nothing about paths here and straightness. So it's just this D function, this metric. Okay, so that's a metric or distance function. And again, this is a more general concept than Euclidean distances and Euclidean geometry that we're used to, like in R2 or R3 or something like that. You can put a distance on just kind of a set X. Okay, so why am I bringing this up? This has nothing to do, this says nothing about topology, right? The reason I'm bringing it up, first of all, because like I said, we're going to talk about distances on manifolds. It's the real reason to talk about distance metrics, but also because we can, if you give me a metric on some set X, I can give X a topology that agrees with that metric. And so am I doing time? Okay. The metric topology, we've actually already seen it in the case of Euclidean space. So R or RD, D-dimensional Euclidean space, we actually already gave that the metric topology when we talked about open balls. Okay, and so I'm not going to rewrite all this, but say I have a metric distance or distance function on a set X, then the topology is going to be built up from a basis set. Remember, the basis is for the building blocks that any union of basis elements gives me all the open sets. Then I'm going to build a basis of open balls. And remember, this is the same notation I used before for Euclidean space. I'm just going to make it a little more general here. This is all points in my set X, such that now instead of Euclidean distance, meaning that norm function, I'm going to say the distance between X and Y is less than the radius R. So R has to be a real number greater than 0. Okay. And so, yeah, so you can have the same picture in mind. I have X, and now I have, I'm going to take, again, what we call an open ball. This means that everywhere I go inside this BXR is going to be less than R distance away from the center point X. But you have to think of this not as a ball in just Euclidean space, it's a ball in just any abstract set that I can put a distance function on now. So kind of just to maybe give a more concrete example that is different from what we've already seen. Let's say we are using Manhattan distance, right? If you are in a city, like where everything is blocks and you can only walk along the streets in a grid, then I can't take straight line distances to everywhere I want to go. Places I want to go, I have to move always kind of like along the axes, the XY axes here. So if I want to go from here to here, I have to move up and then over on the next block to get to that point. And so this Manhattan distance is a distance on the grid. And I can talk about restricting the amount of distance I can travel by some some radius r, and that would give me balls, open balls in this grid space. And you would be able to put a metric topology of open sets on your grid there. Okay. Right. Any questions on metric spaces and the definition of the metric topology we have here? So yes, if I have a metric topology, I very often will just say I have a metric space. I mean, technically a metric space is any set with a distance, but if I want to use the topology, because it kind of comes for free, I don't have to do anything extra. Once I have this distance function, I have this topology. So if I say metric space, very often I mean the topological space. Okay. Let's see. So that's metric space. One other concept here. Let me move over here. Will be another way to get topological spaces from other things that we already have is when we have a subspace of a topological space, we can put a topology on that subspace. So we have something called a subspace topology, and I think this is relevant for the homework. I think you have to answer a question, maybe number 2, that has to do with, I think, both metric topologies and subspace topology, if I remember correctly. Question number 2 in the homework makes you make an argument about these concepts. So subspace topology, the idea is that we have a topological space X already, and now I will use the notation, it's got a topology, just to be clear that it has a set of open sets. And then I take any subset of X, I'll just start like so, Y can be any subset at all. All I need is that Y is a subset of X. Okay, and now I can again get a topology on Y for free. And the way I do that is I take the open sets of X and I look at their intersection with Y. So let's say U is an open set, meaning it's in this collection of the topologies defined as what are the open sets. Then I'm going to define the open sets to be subsets that look like the intersection of open sets in X with elements of with the subspace Y. So this I'm going to define to be an element in TY, and all such things I can form this way will be all the open sets in my Y topology. Okay, so I'm just going to take intersections of open sets in X. So really this kind of piece that overlaps with Y will be the open sets in Y. Okay, and again, I'm going to wave my hands and not prove anything because this isn't a topology class and we're trying to do a high-level overview of topology. I'm going to wave my hands and just say without proof that this is a valid topology. That all sets that look like this, you can prove or you can show, if you think about it, it's pretty easy to show if you want to exercise again, that this would form a topology, this set TY is a topology. Actually, to be fair, I didn't really prove that the metric topology is topology either, so I should wave my hands at that too. If you want to be rigorous about it, you would prove that these metric balls are a valid basis. Again, we had the axioms for what it means to be a basis. So if you want to convince yourself that those satisfy those rules, you can do that. Okay. Okay, so let me take a moment to any questions about these definitions? metric space and subspace definitions are just ways of getting more topological structures without going through a lot of hard work to define it from scratch. You define it from things you already had. Basically, if you had a metric, a distance function, you know, boom, I've got a topology. I don't have to do any work. If I already had a topological space, you gave me a subspace, I say, okay, I don't have to, you know, do a lot of work to get TY. I just say I use the TX elements and just intersect and I'm done. Okay. Let me take a minute. I'm switching all the way back to the beginning here, forward, to motivate a little bit some of what we're doing here with this abstract math, which, you know, we can see is somewhat connected to things we know, like real numbers, but it seems a little bit like, what's the point of all this, you know, abstract generalization of things? So I'll just to take back to the motivation of the course. The picture to have in mind is, again, we have this idea of our data space. And this manifold hypothesis that there's some subspace in our data space where the data actually live. Like if I had images or text or some kind of signals from some kind of system, I imagine that it's not really just filling up a uniform distribution in the ambient, you know, representation I have, like images, for example. It's actually living on this lower dimensional subspace. Okay, so one thing is you can start to see why the concept of a subspace is important. We're going to be always dealing with subspaces when we have real data. The concepts of manifolds we have already mentioned is important because we think of these, a useful model at least of where our data lives as a manifold. That's the subspace of our data space. But I want to mention why all these topological concepts are important. And that is that when you think of machine learning, and I could be talking about neural networks, that's what we're usually talking about these days when we say machine learning, but it could also be other forms of machine learning, whether it's classification or regression problems, what have you. They're all about functions, mappings. Okay, so a neural network is really just a map, always just going to be a mapping. So if you give me this, you know, let's say convolutional neural network, very deep, what have you, it's really just mapping from some input space to some output space. And so the very often the direction you're going in is I take an input space, which is my data, I map it to some output, and that might be a kind of a low dimensional probability vector. I'll just draw this little vector there. And this would be maybe a subset, an element of, you know, k-dimensional Euclidean space or something like that, where I have maybe k classes, and these are just the probabilities of each class, and I'm trying to classify images, right? But the neural network or other classifier, doesn't have to be a neural network, is typically just a very complex, you know, nonlinear mapping from one space to another space. Okay, and so properties of mapping is really actually very critical to machine learning. And what are you doing to the space or subspace that your data lives on as you push it through this mapping? The very simplest thing is, you know, is that mapping continuous? We're going to also talk about differentiability when we talk about manifolds, but understanding these mappings in machine learning and their mathematical properties is sort of a big part of what this class is about. I'll mention there's mappings that also go this way. We'll talk about a lot, and I'll call this G. Now our K won't be a probability vector of different class labels, but let's say this is just a random vector that you generate with a pseudo random number generator. And then you use a neural network to map that back to your data space, and generate random images that look like real images. So these are the generative models, kind of are mappings that go in, I think of it kind of as the opposite direction as a classifier goes in, from a low dimensional space typically to your high dimensional data space. And again, properties of these mappings, when they give you what kind of topology or geometry they give you the output, we have to understand these concepts of topology and mappings, continuity, homomorphisms. We'll have other, like I said, morphisms to talk about that come along the way. So this is why we're doing all of this sort of basic math in the next, from now to the next couple of weeks still. Okay, so just wanted to tie this to, shoot, the board again. Apologies to people on Zoom. Yes, sorry. Was that what you were going to say? Or
Just point to the camera.
okay, yeah, thanks. So any questions about sort of any of these concepts or the motivation of the why we're doing them? The connections won't, the actual concrete connections will be further down the course. So you have to kind of bear with me and Amon for a while we do just kind of a lot of pure math, but keep in mind that there will be a point to it eventually. Okay. Yeah, question?
So I have a tricky question. As you see, Y is a subset of the X. That means Y is also underlying in the topology of the X.
Yeah, come back over here. Yeah, so the subspace topology, X is the setup is X has a topology, and then Y is just the only condition I need, excuse me, is that Y is a subset. Just so throw away the topology for a minute and just say Y as a set is just contained inside of X. And if that's the case, then I can form a new topology. It's really recycling the topology of X and use it to define a topology of Y.
So Y is subset of X is not equivalent. The Y is underlying in the.
Correct. Yeah. So Y does not have to be an open set. It doesn't have to be a closed set, or it has no rules at all. It just has to be a subset, any subset at all. So I can give an example. Again, let's just take Euclidean space, or I'm going to just do R2. Okay. And this actually is a really good example because I'll make a point about what's interesting here. So now let's just take like just any kind of closed set. Like I'll take like a box or a square, let's say, in R2 as Y. So this is X is all of R2. This square here is my Y. Okay, and so notice what's going to happen here is if you give me an open set, whatever this looks like, that's fully contained in the box, then this open set U is an open set in X, but it's also an open set in Y because the intersection is all of U. Now things get interesting though when I get like an open set of X. Again, I should really dash the lines here because this is an open set in the usual topology in R2. So it's like, let's just say an open ball. It intersects in this little piece right here. But notice that, sorry, camera. Notice that the top of this is open in X, but the bottom of this little kind of half moon is going to be a closed boundary in X, but it's going to be open in Y by this construction. Any intersected open set with Y is open in Y. So Y has a closed boundary as far as X is concerned, but as far as Y is concerned, a closed boundary, at least that agrees with the boundary of Y, is still a valid open set. So it's open in Y, but not open in X. So you can get the subspace topology doesn't mean that all the open sets in Y are also open in the parent space X. They can be open in Y, but not open in X. Okay. And yeah, notice Y itself of course, was not open index. It could be any subset you want, really. Okay, any other questions about any of these concepts? I know it's a lot of concepts I'm throwing at you, and I'm doing two things. I'm not doing any proofs of any of them, so you have to either take my word for it or have to think about it more on your own or Google it. You can find like on Wikipedia, all these concepts are proved actually. And number two, I'm giving very limited concrete examples because we have to just kind of cover a lot of stuff. If you took a topology course, you would spend like a whole week on each of these topics and do lots of examples and proofs and things like that. But we're just trying to do topology in 2 days, which is a lot to cover. Okay, there's one more concept in the last 5 minutes that is going to come up on Thursday, just in the definition of what does it mean to be a manifold. And so you can get some very pathological topology, so topological spaces, if you just need to satisfy those 3 axioms of what it means to be open sets. And so there are some, let's call it additional axioms you can add to those axioms to make it more like Euclidean space, to make your topological space more like Euclidean space. So I could say my topological space has to have a metric associated with it. Okay, that would make it more similar to what I get in Euclidean space, for example. A weaker property that's not as strong as having a metric is talking about what it means to be separated in a topology. And so separation rather means that, okay, if I have this topological space, again, capital X, and if I give you 2 points X and Y, like we saw with the ABC, just the ABC set, right? There were some interesting things going on there. If I give you, can I find open sets that contain these points, contain maybe one of these points, but not the other? This is what we mean by separation. So I'll just kind of do the ABC thing again. Like we had ABC, and like something like this was a valid topology. And notice A and B can't be separated. They're always got to be in the same open set, either all of X or AB. There's no way to kind of pull them apart. In Euclidean space, you give me any 2 points. I can always find open balls that separate those 2 points. And so this is what we mean by separation by open sets. And so, and there's different levels of strength in how well you can separate points. Like maybe I can put an open set around one and not the other, and maybe I can do what I'm doing here, which is put 2 open sets around each point, such that one is in one open set, the other is in the other open set, and then U intersect V is empty, so they don't overlap. So that's kind of a fairly strong separability. And this is what we're going to use in manifolds on Thursday. Is we're going to have a little bit more strong separability than just the plain topology axioms. We're going to add this level of separability, and this is often called the Hausdorff property, after Felix Hausdorff. If you can separate points this way, it's open sets. And I like to always give Hausdorff a shout out because he was really the first person in the early 1900s to define topology axiomatically like we have it now today in this most general form. Hausdorff is in some sense the father of topology. He also had the misfortune of being a Jewish mathematician in Nazi Germany. So in the early 1900s to the World War II timeframe. And I really recommend reading his story on Wikipedia, if you will, or somewhere else. Wikipedia has a great biography of him. But he went, if you can imagine being Jewish in Nazi Germany, like his entire career, was persecuted because it wasn't like the Nazis came around by World War II. They were there for quite a while, and there was a lot of anti-Semitism, and he was, discriminated against by even like students in his class. And so anyway, but his wife and his wife's sister were who was living with them, were ordered to report to a concentration camp. And they decided to commit suicide instead. So it's a pretty tragic story of one of the things awful things that happened in that time period. We lost like one of the great minds in mathematics to the Nazis as well. So anyway, I do recommend reading his story. It's a pretty remarkable story, and like the contribution he made, like I said, he invented topology basically as we know it today. Topology had kind of been around by Poincaré, if you know Poincaré, that name, in the 1800s, came up with concepts in like Euclidean space, what it meant to be these topological concepts like generalizing continuity and bringing algebra to topology concepts. But Hausdorff gave it this axiomatic approach that we learned here at last this first couple of lectures. Okay, out of time. Thanks, everybody.